Dear participants, in this session we are going to discuss about linear variable differential transformer. We all call it very commonly as LVDT. Although we have done a detail of this on our theory coursework, but still a brief discussion on the same may precede this experimental session. You see here that basically this is a transformer, and therefore we can say that this sensor is an inductive sensor, and I will be using this document for our discussion. We are indebted to vattelectronics.com for this very comprehensive document. You see here that LVDT is very common and it is extensively used whenever there is a necessity of precision measurement of displacement. So whenever some object is having a translational motion and we are in a need of very precise measurement of its displacement, then LVDT can be a very good choice. Nowadays there are several sort of linear encoders also, but still LVDTs are very much in application. Now, as I had just said, that this LVDT is a very special type of transformer. Just like our generic transformers, here also we have got primary and secondary. The speciality is number one, here there are two secondary windings, and number two, we have got a dynamic core. That means a core that can move. Okay. Now let us see here in this diagram, it has been very clearly depicted that we apply the signal across this primary and we measure the voltage that is developed across these two secondaries. Now here you can see this rectangular portion. This actually signifies the dynamic core. So this core can move. So please do not keep the idea in your mind that we are using an air core device. So in between the windings there is a movable core. And now see, since this core is movable, its position decides ultimately that how much magnetic flux will be linked in between primary and the secondaries. So here we can very easily see that if we are in a null position, that is the core is perfectly at the center in correspondence to the primary, then whatever voltage that will be developed across these secondary windings will be equal and opposite, and therefore the effective voltage that we will be getting across these two secondaries is 0. Now suppose our core is in the extreme right position. So here we can see that magnetic flux linkage or mutual induction will be more prominent in between primary and winding S2, that is right winding. Accordingly, the output voltage will be changed. Another condition can be that this core is in the extreme left position. In such a situation, you can see that this primary and this S1 secondary is now magnetically better coupled in comparison to the magnetic coupling between P and S2. So flux linkages will be more in between P and S1. So again the voltage will change. Most important is we get different polarity, opposite polarity of voltage. So this concept is very important, and by observing the effective voltage and polarity, we can well determine the displacement, I must say a very precise displacement of any object. Suppose we have to determine displacement of any particular object. What we need to do is we need to couple it to the core so that it can be smoothly displacing the core, and the core will get displaced along with the body. So if such is the situation, then you can well find that the movement of the object will be ultimately resulting in different values of voltage across these secondary windings S1 and S2, and that ultimately we have to measure. Now you see here that this is the ideal graph for an LVDT shaft variation, where you can see the x-axis that signifies, or in x-axis we plot the displacement, and in y-axis we plot the output voltage. As you can very easily see, in the null position the output voltage should be ideally 0. There might be some hysteresis, and in while the body is moving in the positive x direction, you will have values, and ideally continuously increasing values, gradually increasing values, and then there will be a saturation. That depends on the construction, that when this will be saturated, that is depending on the construction or the range of the LVDT. Now while it is moving on the other side of the null position, you will again find the values, but now that will be having an opposite polarity. We will see that. You see that whenever we are talking about opposite polarity, right, you can say or ask me one thing, that where is the opposition of polarity, because it is both in the same axis. Okay, because shaft position you can see is in x-axis, and output voltage is depicted in y-axis. Then where is the opposite polarity that is reflected? Normally it is, whatever we are talking about here is the differential AC output. In AC you will not find that. But what is actually done, that for measurement purpose and especially to get the benefit of this opposite polarity, the signal, output signal from an LVDT is conditioned, and we are more interested towards having the DC voltage. So whenever we have the DC voltage, we will have the signal conditioning is done in such a manner that we will be having opposite polarity signals. The signals will be just mirror image, only with the opposition in polarity. Okay, so with this much brief, let us start with the experiment. You can see we will be using this generic setup for various experiments of sensor. This is Scientech Indore Make 2311 kit number, which is a composite kit and a very utility kit to have comprehensive study of sensors. You may find that there are several blocks in this. As you can see here, you have onboard plus 12 minus 12 supply, plus 5 minus 5 supply, plus 3.3 volt supply, and definitely ground. Then you have many utility blocks. You can have a current amplifier, you can have a power amplifier, there are potentiometers, sorry, differential amplifier, inverting amplifier, non-inverting amplifier, instrumentation amplifier, high pass filter, low pass filter. You have voltage to frequency converters, you have frequency to voltage converters, I to V converters, V to I converter. You can have current source, you can have square wave generator, a buffer, LED indicator, buzzer, and an LED bar graph. Also, as you can find, there is a screen on which we can have complete manuals, the steps to perform any experiment, and we can plot the data online. So all these facilities are available. Definitely we will not plot the data on the LCD. We will be plotting it on our multimeters for a sound understanding. Now in order to send the signals inside this smart screen, actually we have got some ADC input. We have got some DAC outputs also. Digital inputs are there, digital outputs are there as well. Okay. So with this much discussion on the board, we can find one thing, that there are several blocks which are of great utility. For what? You see that sensors can be of different types. And at this point, let us look a very brief overview of the sensors, what they actually do. These sensors, they actually give you understanding of what? Physical or chemical situations. You can have several physical situations that you might be interested to measure. What they can be? Very simply, you want to measure time. For that, you can see this clock that shows you the time. If there is no clock, you can think that you cannot know what is the time, how the time is passing. So you can say that yes, clock is the sensor of time with its least count of maybe 1 second. In that way, you can say like that. Or we can say, what are the different physical measurements? You might be interested in measuring temperature of an object. You might be interested in measuring the amount of liquid that is flowing through a pipe. Rate of flow of that liquid through that pipe can be another object that you might be interested to measure. You want to know what is the level of water that is stored inside your overhead water tank. You might want to know what is the pressure of air that is there inside your tire of the bike. So all these things you want to measure. These are all different physical situations. So whenever there is a physical change in some physical parameter or change in some chemical parameter, we are interested to know how much change has taken place. You see, even whenever we are feverish, we want to know what is the condition of our body by measuring the temperature of our body. So it is that important. Science of sensor and transducer is that's why so important. Now sensor helps us to know this. You can see whenever the leaves of a tree that are in motion to and fro like that, you can say that yes, there is flow of air. But what is the airflow rate? Whenever such measurement comes into the figure, sensors are inevitable. They actually change that physical or chemical stimuli or change into some format. So they translate that change into some format that we can understand. Maybe there can be some visual indication, some audible indication, maybe some reading in a meter, maybe some bar graph display. All these things are there. Now, we are more interested to have electrical signals more commonly because electrical signals can be easily recorded. You can easily measure it by very low cost standard devices like multimeters. We are very familiar with the terminologies voltage, current, resistance, all these things. So therefore, sensors that can give us output in electrical terminology, they are very popular. And these family of sensors, they are called as transducers. So normally transducers, they give you an electrical output. Maybe they can use a bridge for that. The output of that transducer can be so feeble, such a feeble electrical signal is generated out of that it is unable to read even. So for that you can have an instrumentation amplifier, a bridge, or some other sort of amplifier. So as you can find that not only the sensor, you require some additional element in order to make that signal readable. Because if your signal is very small, you have to amplify it. Now suppose we are considering the example of radio. So you see that in radio, for a particular channel, you want the data of that channel only. But you are getting the ether signal which is containing data from various channels. So you have to have some sort of filtering so that you can get exactly what you want, what you require. So you need a filter. It may so happen that output of your sensor is voltage, but you want the output to be in current. It may so happen that output of your sensor is frequency, but normal multimeters, they are unable to read frequency, and you want that output to be directly fed to some data acquisition system which accepts only voltage. So you have to change your signal from frequency to voltage. So this particular science, it is a very vast subject in itself, and it is called as signal conditioning. This subject is equally important as that of the subject of sensors and transducers, and instrumentation actually collaborates these two verticals, where we need to know about sensors, we need to know about transducers, we need to know about signal conditioning. Because suppose we are using a thermocouple for reading a temperature. Now what is the output of the thermocouple? Its output is in millivolt. So it generates a voltage. On the other hand, if you are thinking of an RTD, resistance temperature detector, its output is in resistance. So one is a passive type of device and the other is an active type of device. So again this classification is there. Now see that if suppose you have applied a thermocouple to measure the temperature of a metal block, and you have applied some heat to the metallic block, maybe through a heater. So what will happen? The temperature of the heater, that metallic block will increase because it is in contact with the heater, and at the output of the thermocouple you are seeing 0.1 volt, 0.2 volt. I am just saying for example, yeah, 0.3 volt like this. So should you be in the conception that the temperature is 0.1 degree centigrade, 0.2 degree centigrade, or 0.3 degree centigrade, it will be completely wrong. You are getting an electrical signal that is proportionally changing with the temperature. Now it's another objective to translate that change in millivolt. Okay, so you are having the temperature in terms of millivolt, change in millivolt, change in temperature to change in millivolt. Now you have to take that change in millivolt to respective value of temperature. So again you need to do some sort of electronic manipulation with the signal, or electronic negotiation with the signal, electronic modulation of the signal, so that you can exactly know what is the temperature through the thermocouple. So here you need to calibrate your device. For 0 degree centigrade, how much is the voltage? For 100 degree centigrade, how much is the voltage? Is the change in voltage completely linear? If it is linear, fine, it becomes easy for you. But if it is a non-linear device, then it is not that easy to just connect a meter and directly go for a linear calibration. So these things keep on going more and more and more complex. Fortunately, we are now going to study LVDT, which is a linear device, and still we will be using some signal conditioning. I will be just discussing the same, but I will not get into the detail. And now I hope that you have understood that why so many blocks are there. You can see this block, all these blocks are one or other type of signal conditioning circuit. Now, if we have to develop the signal conditioning circuits, definitely they are also part of experiments at your latter course. But right at this moment, if we start on developing the signal conditioning circuits, then we might get short in studying of the sensors. So therefore, all these blocks are given. You have the input, you have the output. So just we will be using these things as black boxes for seeing the behavior of the sensor. Now see here that all these power supplies are given so that we can feed adequate power to the passive sensors. Okay. So now with this much discussion, let us see how does this LVDT actually look like. So I will take the LVDT here. You can see that this is actually the LVDT, and this portion you can see this is the shaft. I will be just rotating this screw gauge, and you can see this is the core, right? This is the core. It is moving. Now I will just show you that this is actually a spring loaded mechanism. This is a spring loaded mechanism that couples the primary and secondary through magnetic flux. Now you see here that how many watts should I expect out of this sensor? Okay, normally as we have discussed in our theory coursework, that typically a sensor should have three watts, one for the supply, one for the ground, and other for the signal. This is very common in case of especially digital sensors like proximity sensor, photo eye sensors. But here, please remember that we are working with a transformer. So transformer cannot work on DC definitely. So what we require? We require AC to be supplied. Now let us see how many terminals are there. So it is difficult a bit to show everything. So you can see this wire is there. which is coming out of the LVDT, and we can very easily find that you see there are 6 wires, 2 yellow, 2 red, and 2 of them black. Why 6 wires? Now see that very intuitively you can say that yes, 2 wires are for the primary winding, perfect. 2 wires are for secondary 1 and 2 wires are for secondary 2. Absolutely correct. This is the thing. Now you see, let us look at this board very clearly. We have got plus 12 volt, we have got minus 12 volt. We have got plus 5 volt, we have got minus 5 volt. Where is an AC supply on the board? Definitely I am not talking about 220 volt, but I am talking about a stepped down AC supply, because that is required definitely for this, you say, operation of LVDT. Since it is a transformer, it can never run on a DC. So for that we need a very specially designed signal conditioning board. So this is the board that we will be using, and now I will be connecting this. So there is a platform for this, we can mount it. You can see once you have mounted it, this pin number 1, 2, 3, that becomes input to this board, to which we have to connect plus 12 volt, minus 12 volt and ground. So ultimately it is the purpose of this board to convert this DC signal to AC signal that is required for the LVDT. Now again, output of these two secondaries, S1 and S2, you can find S1 and S2, they will be in AC. Again, we will be getting the output of that across pin number 10 and pin number 6. So now what I am to do, I am to give necessary supply. For that, you can see that I have connected this 12 volt to pin number 1. Alright, I have connected this minus 12 volt to pin number 2, and I have connected the ground to pin number 3. Okay, so if this is the case, then let us try to understand whether what we had uh, discussed, that is proper or not. So I'll be using this multimeter. For that, this has got a very good AC voltage range. So you can see I am keeping it in 200 millivolt of AC range, voltage of course. I'll be connecting it to ground on one hand, and you can see I am connecting it to primary. So you can find we are giving an AC signal here. Alright. So in this P1, we are giving actually an AC signal. That is for, you can see here that this is actually a DC that we are feeding this input. DC 12 volt, and here DC minus 12 volt. So here actually we are getting this. So you can see here there is no DC component. Alright. So here we are applying an AC. So you can see here this P1 goes to one terminal of the primary winding. See again. This S1 go to other terminal of the primary winding, and this S2 will go to other terminal of the primary winding. Rest of the terminals we have to directly connect to the ground. So I will now uh, get this camera a little bit closer, otherwise it will be very tough to follow the working of this LVDT and change in the voltages. So I'll be taking the camera a bit near because we are now very sure of the connections. Okay, so it is that. So now we can find that these are the terminals of the LVDT. This yellow terminal is meant for primary. I'm connecting one of the terminals to primary P1, the other terminal to ground. Okay, you can see this black terminal, ground. Then one of the terminals, secondary terminals, is connected to S1. The other terminal is again connected to ground. The another winding is secondary S2 and other terminal to ground. So that's all about the connection. It really makes very easy. So now I will be going for measuring the output in terms of AC first, and I will be, now you can see another point that I wanted to show you, that you see this core, that is the shaft which is connected to the core, this spring loaded shaft. It is again coupled with a screw gauge so that we can make minute displacement possible. You see here that we can measure up to 25 mm displacement. With this 25 mm displacement is possible. So we will be displacing the thing with this only, with the help of this screw gauge, so that we can see smooth operation is there. There is no jerk or something. Okay. So now we will be measuring. I will be just going through a first very fast change, and finally we will be going for the DC measurements more minutely. So here you can see this is an AC voltage we are measuring. I am putting it across so you can see here the effective voltage that has been across the two secondary windings is 0.72 volt at this 0.272 volt AC. This is AC at this position of the shaft. Now you can see as I am changing it in one direction, you can see it is moving towards right. So you see this core is moving towards right. You can see you are having an increase in the voltage. Okay. So we are going towards an extreme. You can find. Now you see I am moving in the other direction. So you can find that it is decreasing. It will never become zero here. You see it is gradually decreasing. I am going it faster. So now you can see I am going slower. So now you can see it has started increasing again. So do you remember that characteristic that we had talked about? This is the characteristic. So on one extreme it is at maximum value, it is not getting to zero. Again it is increasing on the other side. So that is what is happening right now. This is the AC signal. Alright. Now I will be measuring I am more interested towards the DC part. So I will go to this DC value and I will be measuring the voltage across two secondaries. So output is available across pin number this terminal 10 and terminal 6. So now we will be looking a bit onto the values so that we can have a 0 and then positive and negative extremes. So you see here I am taking the core towards right. So the core is coming out from the cavity of this the core that's winding. So you see here, now you can see it is a DC voltage. So this becomes 0. All right. Now here uh, we need to measure. I cannot take the camera closer because that will not give us the entire view. Right at this moment, you see this linear scale. The minimum measurement that we can make with this linear scale is 1 mm. So you can see right now it is 6 mm on the linear scale and it is the count 60 on this circular vernier. All right. So we can say that is 60 into this list count with this vernier that we have to see. So the minimum value of the linear scale, that is the list count of the linear scale, is 1 mm and total divisions in the vernier is 100. So we have to measure in this fashion this 6 mm, that is the value of the linear scale, plus 60 into 1 divided by 100. So here it is 6.6 mm. So what I will do, I will shift through 1 mm in each term. So every time you have to note this 60 mark that is coinciding on the central line of the main scale, and you have to read the reading here. So let me do that. Through that, in that action, in that fashion, I will be rotating, or I will be making a linear displacement of 1 mm. So you can see this is 1 mm and we have got minus 0.06. Another mm minus 0.12. You can see this linearity. This is the linear behavior of this device and how excellent it is. I will go for another mm. You see here minus 0.18, minus 0.18, sorry. Minus 0.24. We will go for another reading. Minus 0.30. So you can see for each mm it is increasing in same fashion in negative axis. Now we will go for 0 again. So you can see it is 0. Now we will be putting the core inside the winding. Okay. Earlier we were taking it away from the winding. Now towards left. So there is positive change. Again, I will go from 60 to 60. So that will be traversing 1 mm. So you can see here 0.06 positive. Another mm 0.12. Another mm 0.18. 0.24. 0.30. Every time you have found here that it is 60 on that line, just to maintain 1 mm displacement in x-axis. So here you can see how beautiful the linearity behavior of this device. So you can also determine that for each mm how much change of voltage is there. So that will be a value that is known as sensitivity of this change in voltage per mm. So that we may perform when we will be performing this experiment in our lab through readings in our graph papers and all the things. But I hope that the concept of operation of LVDT is clear to you. That's all with this session. Whatever confusion that is arised in your mind, do not feel hesitant to comment in the comment box so that we can get back to you in no time. Thank you.